Hello class, today we're going to do chapter 8, Personal Finance, section 8.4, Compound Interest. So our objectives today are to use the compound interest formulas, calculate the present value, understand and compute effective annual yield. Alright, so we'll start out with the definition of compound interest. Compound interest is interest computed on the original principal as well as on any accumulated interest. To calculate the compound interest paid once a year, we use A equals P times 1 plus R raised to the exponent of T, where A is the account's future value, P is the principal and is called its present value, R is the rate, and T is the number of years. So let's look at example 1. You deposit $2,000 in a savings account at Hometown Bank, which has a rate of 1.6%. We want to find the amount A of money in the account after 3 years subject to compound interest, and B, we want to find the interest. Okay, so we're going to find the amount of money at the end of that year and then figure out what amount of money of that final money is the actual interest. So let's look at A about finding that money at the end of that 3-year term. So the principal P is $2,000. We saw that right there in the original problem. $2,000 right there. R is 1.6%. There's your rate, 1.6%. Or, of course, we need to write this as a decimal, and that's where we get the 0.016 from, right there. So T is 3 because we are trying to find it after 3 years. Okay, so that's where our T is 3. Okay, substituting this into the compound interest formula, we get A equals P times 1 plus R raised to the T. So, we said P was 2,000. Then we have 1 plus R, which is our rate, is 0.016. All raised to the third power because it's been 3 years. So, we calculate that out. We get 2,000 times 1.016 raised to the third power, or approximately $2,097.54. Okay, so that's how much we've made after 3 years. But remember, our initial deposit was $2,000. So this will help us answer part B. Okay. So part B says the amount in the account after 3 years is $2,097.54. So we take the difference of this amount and the principal to obtain the interest amount. So we'll take that $2,097.54 that we calculated in part A, subtract that from our initial investment of $2,000, and we see that over 3 years we have made $97.54 in interest. Alright, so that's compound interest paid just once a year. Now let's look at compound interest paid in times a year. If you deposit P dollars at a rate R in decimal form, subject to compound interest paid in times per year, the amount A of money in the account after T years is given by A equals P times 1 plus R over N raised to the NT. A is the account's future value, and P, principal, is called its present value. Okay, so we've got this new formula, and this new formula basically compounds it by a certain number of times per year. Alright, that number of times per year is the N in the formula. Okay, it's very similar to the original formula we had, but we have an additional N here that we have to worry about. So let's look at an example of how this works. You deposit $7,500 in a savings account that has a rate of 1.2%. The interest is compounded monthly. So instead of being compounded once a year, we're compounding monthly here. How much money will you have after 5 years? Okay, and then we'll also find the interest after 5 years. So, principal P of $7,500. The R is 1.2%. That's just directly from the problem, right? So your principal is how much you initially invested. Your rate is given to you as well in the initial problem. Remember, we have to write it as a decimal. So here is a decimal at 0.012. T is 5. Okay. because we are doing it over 5 years, and n is 12. Okay, now here might take some explaining. Here n is 12, right? Because we're compounding monthly. There are 12 months in 1 year. That's where the 12 comes from. Okay, and this compounded monthly, we have to break it down in terms of a year. Okay, so the n here is 12. We are compounding monthly, so we're compounding 12 times per year, since the interest is being compounded monthly. Substituting this into the compound interest formula, we get A equals P times 1 plus R over N to the NT equals, okay, then we just do a simple substitution here. The P was 7,500 times 1 plus, the rate here was 0.012. That's just directly from right here in our problem that we found based on the 1.2% rate, divided by the n, which we determined to be 12 because we were doing it monthly. And then we'll raise that to an exponent of nt, so 12 times 5. Okay, 12 times the number of years, which is 5 years. We computate all that out, and we find that after 5 years, our $7,500 has now grown to $7,963.54 approximately. Okay, so in part B, we want to look at how much of that is interest. Okay, so the amount in the account after 5 years, we determined that to be $7,963.54. So if we take the difference of this amount and the principal, the amount that we initially invested, we will then obtain the interest amount. So we're going to take that $7,963.54. We're going to subtract $7,500, and that gives us our interest here of $463.54. So the interest that we made after 5 years on this investment of $7,500 at that 1.2% interest rate over 5 years, compounded monthly, is $463.54. All right. Now you might be thinking, okay, the more you compound, the more you make. And this is indeed true, but it might not turn out to be as much more as you think. So let's look at if we compounded it continuously, because we started with the year. That's one time a year we compounded. Then we compounded monthly. That's 12 times a year, okay, based on that interest. Now, if we sped that up and just continuously compounded, let's see what that would do. So some banks use continuous compounding, where the compounding periods increase indefinitely. So after T years, the balance A in an account with principal P and annual interest rate R in decimal form is given by the following formulas. For n compounding periods per year, we have the formula A equals P times 1 plus R over N raised to the NT. That's the one we used in that previous example we just went over. But we also have the continuous compounding formula for number 2. That is A equals P times E raised to the RT, where E is just a number. You can find that number on pretty much any calculator that you use, especially like a TI 8384. Okay, E is just a number, right? Because what we find is if we take the limit of this as n approaches infinity, it approaches this number E. Okay, but that's beside the point of this class. If it asks you to compound continuously, you will use the formula A equals P times E raised to the RT. If it asks for a certain number of compounding periods, say monthly, daily, weekly, biannually, you would use A equals P times 1 plus R over N raised to the NT. Alright, so let's look at example 3, choosing between investments. You decide to invest $8,000 for 6 years, and you have a choice between 2 accounts. The first pays 2.5% per year compounded monthly. Okay, so that's 12 times a year, right? The second pays 2.49% per year compounded continuously. Which is the better investment? Okay. Now, the better investment is going to be the one with the higher balance at the end of the 6 years. I think we can all agree on that, right? So we want the most money after that period of time. Let's see which one's going to give us the most money after that period of time based upon the formulas that we have. Let's start with the 2.5% compounded monthly. So we're looking at this 2.5% account right here. All right, we're going to use the formula for compounded monthly, or compounded a certain time per year. That's A equals P times 1 plus R over N raised to the NT. Now we're investing $8,000. We're going to multiply that times 1 plus our interest rate, which is 2.5%, right, for that compounded monthly period. Okay, we do have to write that as a decimal, so we have 0.025 all over 12, because we're compounding monthly, and there are 12 months in 1 year. So that's why we divide by 12. Then we raise that to the 12, once again from the monthly. 12 times 6, because we're compounding over 6 years, right? So is that right in the problem as well? If we do the math on that, we wind up with $9,293.20. So the balance in this account after 6 years is $9,293.22. Now, let's find the balance of the other account, where we are looking at compounding continuously and having a rate of 2.49%. A really, really close rate, slightly lower rate, but we're compounding a whole lot more times. So let's look at this 2.49% account. This 2.49% account. Remember, for the compounded continuously, we have to use the formula A equals P times E raised to the RT, sometimes called the PERT equation. All right, so we're still initially investing that $8,000. We're going to multiply that times E raised to our rate here. Our rate for this continuous account was 2.49%. We just wrote it as a decimal, 0.0249, and we're going to multiply that by the number of years, because that's our time T there. So we multiply that by 6. When we calculate this out, what we see here is that after those 6 years, we have $9,289.10. So the balance on this account after 6 years is $9,289.10. Okay. Now let's flip back. Compare the two numbers: 9,293 versus 9,289. Okay. Of course, you got some cents in there as well, but I think we can clearly see that the better investment here is the 2.5% monthly compounding option. Okay. So just because you compound continuously doesn't mean that you're going to make more money. Here the rates were slightly different. We had a 2.5 versus a 2.49, only 1/100th of a difference, right? But here the monthly won out, because that 1/100th was just enough to overtake that compounding continuously option. If they were both 2.5%, then compounding continuously would have won. But because of that disparity of that 1/100th of a percent, it made all the difference. All right, let's look at calculating present value. If A dollars are to be accumulated in T years in an account that pays rate R compounded N times per year, then the present value P that needs to be invested now is given by P equals A over 1 plus R over N raised to the NT. Now that is just a back solve for our equation that we had. Okay, so that is just a back solve for P for that original equation we had right there on the lower part of here that we've been using. The A equals P times 1 plus R over N to the NT. That's just a back solve for it, and I did a terrible job of circling it. All we did is back solve that equation for P. Okay, so we can find what we need to invest now for what we want later, given this equation. So let's do that. It says how much money should be deposited in an account today that earns 6% compounded monthly so that it will accumulate to $20,000 in 5 years. Okay, we have all the pieces we need. Now it's just about plugging it into the equation. That's all we got to do. Okay, we're going to use that present value formula that we just went over. Right? If you need to write formulas down to keep track of them, by all means, go on ahead and do that for me. I don't care if you have your little formula sheet right there to keep track of them. Ain't a problem at all to help you learn. That's all we want to do, is learn and figure out how we're doing to use this. Okay. Now, breaking it down here. Okay. A is $20,000. That's what we want to accumulate to in 5 years. We don't know what we need to invest in order to accumulate to $20,000 in 5 years, but we know that that's what we want at the end of 5 years. We also know that this account is going to earn us 6% compounded monthly. Remember, monthly is 12 times a year. Keep that in mind, right? So, A is 20,000, R is 6%. We do need to write that as a decimal, 0.06. N is 12, and T is 5 years, because clearly this will be done in 5 years. Problem says that clearly as well. All right, let's plug this in. P equals A over 1 plus R over N raised to the NT. We still do our substitution. A is 20,000 over 1 plus 0.06. That's our rate divided by N, which is 12. Raised to the 12, which is also our N because it's monthly, times 5 because we're done after 5 years. And this is what we see when we simplify in our calculator. We get 14,827.4439. We round it to the nearest cent here. Or we're just going to round it up to the nearest cent, it looks like here, because you'd rather be over your budget than under your budget, right? We want to make that 20 grand at $19,999 might not do it for us, so we're just going to round up to the nearest cent. So approximately $14,827.45 should be invested today in order to accumulate $20,000 in 5 years. Now that $20,000 won't all be interest. It'll include your initial investment, right? But you'll be able to bring that $14,827.45 up to 20 grand in 5 years in that 6% compounded monthly account. It's all about the formulas and the calculations. All right, the effective annual yield, or the effective rate, is the simple interest rate that produces the same amount of money in an account at the end of 1 year as when the account is subjected to compound interest as a stated rate. Okay, so let's look at and try to understand what we're talking about here. We are going to deposit $4,000 in an account that pays 4% interest compounded monthly. Let's find the future value after 1 year. Okay, and then we're going to use that future value formula for simple interest to determine the effective annual yield. All right, here's what we're doing here. Okay, so you've got something that's compounded at a non-standard rate here. We're compounding monthly, daily, weekly, hourly, whatever. What we're effectively doing is we're going to take that, calculate out what it would be, and then back solve to see what it equates to as an annual simple interest, okay, for your annual yield. So you can kind of compare those rates. It's all about comparing rates when you're looking at doing different things in life, whether it be buying something, borrowing something, or letting somebody borrow your stuff. Okay, so while it might seem like a small percent rate for something monthly, it might add up to a large percent rate for something annually. And we want to know how to convert between the two. I hope that helps kind of explain what we're trying to do and the reason for it. So let's look at it. We're going to use the compound interest formula to find the account's future value after 1 year. Right? That is the A times P times, or A equals P times 1 plus R over N raised to the NT. All right. We know that our P here is that 4,000. We know that our rate is 4%, and we're compounding monthly. We're looking at after 1 year for part A. Remember, monthly is 12 times a year, so that's why we get the 12 that we use here. So we're looking at $4,000 times 1 plus 0.04 divided by 12, all raised to the 12 times 1, because we're just doing 1 year. That's going to give us $4,162.97. Okay, that's what our future value after 1 year would be. Now, the effective annual yield is the simple interest rate. So we use the future value formula for a simple interest to determine your rate R. Okay, so we're looking, okay, this is what we're looking at. So the formula we're going to work with here is A equals P times 1 plus RT, because that is our 1 year interest rate formula. Okay, simple interest rate right there. We're going to take the value that we wound up with after our monthly compounding, our future value, which is from part A, our $4,162.97. that is going to equal $4,000 times 1 plus R times 1. Okay, because we're just looking after 1 year. So our time t here equals 1. Oops. I'll just rewrite it instead of trying to erase. T equals 1 here. That's where that 1 came from, right there next to the R. P was our initial amount invested. Remember, that was $4,000, and that $4,162.97 came from part A. We are solving for R. We want to know what the effective rate for 1 year would have been. Okay. So, what we do is back solve. We distribute the 4,000 to both terms. So I distribute it to the 1, and I distribute it to the R times 1. Well, R times 1 is just R, and R times 4,000 is just 4,000 R. I subtract over the 4,000 here. Okay, that's what leaves us with the $162.97 equals 4,000 R, because obviously that cancels. We divide by 4,000 on both sides to get rid of that 4,000 there. That'll cancel. Also divide this by 4,000. So R is going to equal that 162.97 divided by 4,000, or essentially 4.07%. Thus, the effective annual yield is 4.07%. That means that an account that earns 4.07% interest compounded monthly has an equivalent simple interest rate of 4%. That's all it means. That's all it means. So, that's it. It's pretty simple. That completes this particular section. Please go ahead and start the associated assignment or go on to the next lecture. If you have any questions, please don't hesitate to reach out to me by email and ask. I'm always available. I appreciate you watching. I look forward to teaching you the next lecture.